Hi, welcome to R2E, and in this video we will talk about an example where we will discuss the Klein-Gordon equation, and we will write an Lagrangian. We will take a given Lagrangian, that is for the Klein-Gordon field, and we will try to use Euler-Lagrange equation to get to the equations of motion. And the thing about today's lecture is that we will not directly use the Euler-Lagrange equation for fields, but what we will do is we will use from the first principle. We will try to derive this Klein-Gordon field equations. Okay, let's start. So the first thing is the Lagrangian for the Klein-Gordon field is given as half y naught squared minus of grad phi squared by 2 minus of v squared. Okay, great. So this is the Lagrangian, and I want to get the equations of motion from this Lagrangian. So let's just first write the action, that will be dt dqx. Definitely this is not Lagrangian, this is Lagrangian density, and that will be 1 by 2 y dot square minus of grad phi square by 2 minus of m squared. Okay, that seems fair. Now we have s, and s is a function of phi. This is not a function, this is a function. And what we'll do is we will take a variation in phi as phi equals to phi plus epsilon, and we will put some boundary condition on the epsilon so to get the equations of motion. And we will see in the later sections that different boundary conditions on phi can lead to different equations of motion. Euler-Lagrange equation is a very specific case where we demand the variations to end on the boundaries, but it is not necessary always to have the variations to end on the boundaries, and depending upon whether they end or not, we can get different kind of things, different topological effects and different kind of equations of motions. So alright, but for now, or for these videos, we will try to we will try to demand the variation to end on the boundaries, but I'll show you how the boundary terms arise and how you could not have the boundary terms to produce it. So we will derive the equations of motions from the first principle. Okay, so this is going to be quite a long of calculation. So let's see how well I do, and let's get started. Okay, so I have phi goes to phi plus epsilon. So my s plus phi epsilon should be I'll just put say d4x, I think d4x should work. So I'm putting 1t into the x0, let's say it's t, and this is for a rough notation. Don't judge it for dimensional purposes. Dimensionally there is still t, proper t. Okay, so this will be 1 by 2 phi dot plus epsilon dot squared minus of 1 by 2 grad phi plus grad epsilon squared and minus of m squared phi plus epsilon whole squared. Okay. Now let's just do one thing. So what we can do is we will x and that will be, so here it will be 1 by 2 y dot square plus. So what will I do is I'm only taking terms up to epsilon, because I am demanding the extremization of my action. So what I don't need to consider the quadratic terms of in epsilon derivatives at all. I can turn on the epsilon derivatives onto some other variable and get things. But yeah, so I'm not talking about epsilon's higher derivative of epsilons, but only up to the epsilon. So I will not write epsilon dot square here. This is a plus b whole square, so a square plus b square. So epsilon dot square term, I'm neglecting it because I don't need it for extremization purpose. I only need up to first derivatives, up to linear powers in epsilon, not quadratic powers. So this is phi dot square, and then there will be phi dot epsilon dot. Okay, seems fair, and then it will be 1 by 2 grad phi squared, and again so minus of, and 1 will have squared, and there will be y squared. I think there is also a 2 here with epsilon. Let's just check it. Yes, there is also 1 by 2 here. I'm sorry for that. There's a 2, there's a 2. So, and there also will be a 2 here. So this is it. And 1 square. We have term like y times epsilon. Great. It's 2 will be cancelled out. Now you can see this term, and this term. They're actually nothing but the Lagrangian of it. So what can I do is I can separate them. I can separate them into one integral and the rest of the integral, and I can just bring that thing to here. But I can just write del s instead of. So once I'm writing del s, I'm just ignoring this term, this term, this term. So I have taken these terms to this side, and now there is a situation like del phi epsilon minus of del epsilon kind of situation like this, calculus like that, and so we can go ahead. So okay, so we'll have d4x, and now we have phi dot epsilon dot minus of phi epsilon. We have minus of m square. Okay, so what we have now is we have epsilon dot, and we have grad phi, we have epsilon, and square epsilon phi. So let's just write this up there, and we'll do the rest of the things from here. Okay, I think I should clean up, right? Yeah, I should clean up. So yes. So what's my final result till here is that del epsilon variation s is d to the power 4x y dot epsilon dot minus of grad phi grad epsilon minus of n square y epsilon. Great. Okay, so this seems completely fair. And what can we do now is I can del s will be integral, and I'm just not writing, this is just taking space, phi dot epsilon dot minus of integral m square y epsilon. Okay, great. So now what I do is I'll use UV rule here and here. So I have u dv, it should be uv minus of v du. Okay, so let's just do this. So I have phi dot epsilon dot, and there is also a dt. So phi dot epsilon dot, so this will become phi dot epsilon. I take dv to be epsilon dot and u to be phi dot minus of, and v is epsilon, and there will be one more derivative on phi, so that will be phi double dot. Similarly here we will do one more thing, that we will have, okay, so we have, okay, let's grad phi, and okay, so we have grad phi, and then we'll have epsilon, and then also we'll have minus of epsilon and grad square phi. Great. So that works. Okay, so this is fine, and there I don't need to do any things. Okay, so let's just do this. So I can just write this as, so there will be phi dot epsilon minus of integral epsilon phi double dot. Similarly, there will be grad phi. Okay, so there are like boundaries, right? So I can write boundaries b, probably epsilon, again boundaries, and there will be plus here, integral, there will be epsilon, and there will be grad square phi. Okay, so here we are fine, and we have minus of integral Now here is something that where what we demand is that epsilon vanishes at boundaries. So demand that epsilon vanishes at boundaries. So we have minus epsilon, and we will write dot. Let's just bring all of these terms to see the integral. Minus epsilon by dot and plus epsilon m square phi, and here is minus of m square phi epsilon. And as we said, we want to demand this integral to 0. So now here we have an equation of motion. Then you can take epsilon here and write double dot plus m square phi square phi. Okay, great. So for this integral to vanish over all its range, all its domain, this integrand should vanish. So this implies that phi double dot minus of plus sure. I'm not sure. Okay, I don't think there should be plus. There should be a minus here, and there should be plus here. Yes, so there is a minus and there is a plus. M square phi square equal to 0. And this is what we call as equation of motion for Klein-Gordon equation. This is Klein-Gordon's equations of motion. Okay, so we saw that we got the Klein-Gordon equation here, but that was from first principle, and we also derived the Euler-Lagrange equation, and I think we should also give it an attempt to see how fast we could get this result directly from the Euler-Lagrange equation. Before that, just to tell you, the another form of this equation, most of the time we just write as del squared phi plus m squared phi equal to 0. So this is how also one tends to write the famous Euler-Lagrange equations. So not Euler-Lagrange equations, the Klein-Gordon field equations, I'm sorry. And yeah, so they are del square. So we could define appropriately del square as however you want to do. The del square is defined appropriately so that you get these equations. Alright. So now what am I supposed to do is, so what I'll do is I'll again take up that same Lagrangian, but this time I will directly apply the Euler-Lagrange equation and we'll see the result. Okay. So let me just erase this first. Okay, so this is what we have, and we just write the Lagrangian first. Okay, so we'll write the Lagrangian. So the Lagrangian now written as 1 by 2 and mu del mu phi, and this is del mu phi, yes, and minus 1 by 2 m squared phi squared. Okay, so fine, we are here. Now this is our Lagrangian. Now you might say this is a little different from what we have written earlier. Well, actually no, it's not that much different. This is just a notation thing, and this is actually a Minkowski matrix. So what we'll do is it will change the indices from like lower indices to upper indices. So like if I just write this as without the Minkowski matrix, that will be 1 by 2 del mu phi minus 1 by 2 del squared phi squared. Okay, so what I have done is this Minkowski matrix has turned this indices, that index that is lower to upper. That's all we have done. Anyways, so what we'll do is, so we'll just take up this Lagrangian and we'll apply our Euler-Lagrange equation directly to it. So what our Euler-Lagrange equation is? Euler-Lagrange equation is del mu del L upon del mu phi, okay, and minus of del L upon del phi, and is equal to 0. Okay. So first of all, let's evaluate this component del L upon del phi is nothing but minus sorry for this is minus of 1 by 2 m squared times 5 cancels, and it is minus of m squared 5. Okay. Now we have mu del upon mu e. So we take up this object for there. So we have mu derivative of first function, that is phi, derivative of first function, and second function, sorry, first function, the second function will have delta mu minus of, sorry, plus delta phi mu. Okay, so I think that's fine. Exactly. So this is what will happen. Yes. So if you contract it properly, what you get is we get so phi will be here, and there will be 1, and this will be del mu phi. Okay. I think it should be del phi. Check. Okay. Sorry. This index should go up. So that will be del mu phi. Okay. We have a lower index here, so and I have this quantity. So this is equal to del mu phi, and now we have del mu phi, and there we had this minus. Okay. Oh, right. Minus of m squared phi. This is del mu phi plus m squared phi. So you would see how fast we again reached our result. So all we did was we just evaluated these quantities and we reached at a result Klein-Gordon field, Klein-Gordon field equation. Okay. This is the equation of motion of Klein-Gordon field equation. You can also write it as like in the notation like this square bracket, square was, this is called Euler-Lagrange, plus m squared. There's a phi outside, and this is equal to 0. So this is the Euler-Lagrange, this is m squared plus phi equal to 0. So this is also these two are the same forms, and here essentially we reached the solution, the equation of motion of the Klein-Gordon field. And to be very interestingly to tell you that Klein-Gordon field is nothing, it's the, what should I say, it's the easiest Lagrangian we have, the simplest toy problem to do the examples in quantum field theory. And essentially your Klein-Gordon field equation is actually a free particle in relativistic quantum mechanics. So when the free particle is moving at a speed nearly equal to the light, this is how we go around. This is the equation of motion we follow. But in another set of videos, that is probably the next video, we'll go about talking about the Lagrangian for the Maxwell's equation, Maxwell electromagnetism. So we'll take up the Lagrangian for Maxwell electromagnetism, and then we will again do the probably not the earlier exercise of deriving the Maxwell's equation from the first principle and to check. More specifically, even if I wish to do that, probably I will not do that on board because the questions are lengthy. I have to see if I can manage it or not. If I do, I will do that on using my iPad and MacBook. And but we will certainly discuss how to get Maxwell's equation from Euler-Lagrange equation. That will be very fast. And probably after that we will move on to the Neither's theorem. We will discuss the symmetries and Neither's theorem. What are symmetries, how symmetries emerge, and we will also see how symmetries tend to emerge in this Klein-Gordon equation, Klein-Gordon field, and if possible, also the Maxwell's electromagnetism. But before that, probably we will also discuss the Hamiltonian formalism, like how to have Hamiltonian for fields, and we will again write this Klein-Gordon equations of motion and also the electromagnetism and Hamiltonian formalism. And what's very interesting about Hamiltonian formalism, it's really very special in the sense that we say time and space have the same stature in modern physics or in a lot of theories. But in Hamiltonian formalism, you will essentially realize that time and space are not the same thing. They are still, you especially need to actually take time derivatives in Hamiltonian formalism when you are doing this. And that will be more explicitly clear in electromagnetic field equation when you will write for Maxwell's electromagnetic equations from the Lagrangian for Maxwell electromagnetism. So okay, so till then, bye. See you in the next video.